The fundamental theorem of algebra. Now, I have to warn you, your book's version will be slightly different. I kind of combined two theorems to make the fundamental theorem just to simplify things. That's what we're talking about today, the fundamental theorem of algebra. The goal is to find the zeros of a polynomial, pretty much the same goal as in the last section. So what does the fundamental theorem of algebra say? It says that any polynomial with degree n, now n is going to be a counting number, right? Like 1, 2, 3, 4, blah, blah, blah. With complex coefficients has exactly n zeros, as long as you count multiplicities. So very easy to understand, and people knew about this for probably hundreds of years, but it wasn't until Gauss proved it that there actually existed some rigorous way of showing it's true. He proved it when he was like 19. His proof wasn't quite perfect, but for a 19-year-old, it was pretty good. Anyway, you don't have to worry about proving it. We're just going to use the theorem. Okay, so we're going to find the zeros of p of x equals x to the fourth minus 3x squared minus 4. So my suggestion is to first list the possible rational zeros. It gives you a starting place. So to list the possible rational zeros, we find the factors of two things. What are they? We want to find the factors of what two numbers?
The first and the last.
Yeah, actually, I do the last first.
The last and the first, sorry.
Because it's the factors of -4, the constant term that'll be on top when you form the possible rational zeros. So I like to do that one first. So what are the factors of -4? And you include the plus or minus on the outside, curly bracket. What are the factors of -4?
1, 2, 4.
1, 2, and 4. Plus or minus on all of them, right? And then the factors of what else? 1. Oh, that's not very interesting. Plus or minus 1. So actually, the factors of -4 are your PRZs, right? Your possible rational zeros in this case, because the lead coefficient was 1. So once you notice that, you don't need to show this much work, at least when your leading coefficient is 1. So there's your possible rational zeros. Now, at this point, if you don't have a graphing calculator, you could just try. There's only 6 of them, right? You could try them using synthetic division to see which ones work, and it wouldn't take that long. But the calculator does make life easier, so let's use it. And then I'm going to graph it on a standard screen, at least for now. If you need to make adjustments, you can. Okay, there we go. So, okay, according to the fundamental theorem, how many zeros do you expect to have? 4, perhaps including multiplicities. How many real zeros do you see based on the fact that they correspond with the first coordinates of the x-intercept? Looks like only 2, even if you include multiplicities, because it looks like it passes right through, in both cases, in both intercepts, it looks like it passes right through the x-axis, straight through. There's not even a bend in it. When there's a bend in the curve, you might suspect that the associated factor with the x-intercept, the x-coordinate of the x-intercept, the 0, in other words. If there's a bend in the curve, you might suspect that the associated exponent is like 3 maybe, or 5, or some odd number. But when it goes straight through, you expect the multiplicity on the 0 to be 1. So it sure looks like there are just 2 zeros, real zeros. But that doesn't tell us about complex zeros, does it? Okay, so which 2 does it appear that they are out of our list of prime suspects from the PRZs?
Positive and -2.
Sure looks like positive and -2. Let's verify. So how do we verify? Good old synthetic division. What am I going to put up in the corner? Okay, start with 2. That's fine. And then across the top? 1, 0, -3. 0. Do you guys see where the zeros come from? Yeah, placeholders for the x cubed term and the x term. Okay, bring down the 1. What goes here? 2. What goes here? 2. What goes here? 4 here. 1 here. 2. 2. 4. As expected, we get 0. And the beautiful thing about this is we're pretty darn positive it's going to be 0 for the remainder. So you just got to find your mistake if you don't get it, right? And you can even check on the calculator, plug in 0. And you know, when you hit the trace button on the calculator, plug in 0, make sure the y value is 0. Okay, so on the remaining quotient, the coefficients of the remaining quotient, we're going to perform synthetic division again. What do we put up in the corner? We want to verify -2 is a 0. Okay, bring down the 1. What goes here? -2 times 1 is -2. What goes here?
0.
0.
1. -2.
And of course, 0. So this wasn't just an exercise. Your calculator is not going to help you find the remaining zeros. But the quotient that remains will contain them. So you had to do the synthetic division anyway. It's not just to verify that plus and minus 2 are zeros. You had to do the synthetic division to get the remaining quotient down to a quadratic. That's the key, because we have the quadratic formula if necessary. So what quadratic do these remaining coefficients correspond to? So the quotient, the remaining quotient is x squared plus 1. And to find the zeros that x squared plus 1 contains, the remaining zeros that the original p of x contains, in other words, what do we do with x squared plus 1?
Solve for x.
Set it equal to 0, yeah, to find the remaining zeros. And we don't need to use the quadratic formula here. This is another one we can solve just by solving for x squared first, right? X squared equals -1, so what does x equal? Plus or minus I, right? So you take the square root of both sides, you get plus or minus square root of -1, which by definition is plus or minus I. So can you list the zeros for me?
Plus or minus 2, plus or minus I.
So how many are there altogether? 4, which is exactly what we expected from the fundamental theorem. 4 zeros. Okay? Make sense? Now, I, plus or minus I, don't correspond to anything on the xy plane when you graph it, which is why it didn't show up in the graph. So your calculator only goes so far. It's only so useful. It helps you find real zeros of a polynomial. It doesn't say anything. It doesn't help you as much with irrational zeros, that is. And it certainly doesn't help you at all with complex, although you can do some things with complex numbers on your calculator. Okay, let's try another one. What would be the factors in this one? P of x equals 4t cubed minus 10t squared plus 4t plus 5. What would be the factors of the constant? Plus or minus, whoops, I've left a little bit out. Yeah, the factors of the constant, factors of 5, and of course plus or minus 1 and 5. What would be the factors of 4? Plus or minus 1, 2, and 4. So what would the PRZs be? Plus or minus? Okay, form all the fractions you can with either 1 or 5 as the numerator and 1, 2, or 4 as the denominator. So many different combinations, but it's finite. There's not that many. What are they? So just start with the 1 in the numerator and then create 3 fractions with 1, 2, or 4 as the denominator. So plus or minus 1 over 1, which is 1, and then what are the other 2? 1/2 and 1/4. You've exhausted the 1, this one right here, in your numerator, so start with the 5. So either 5 over 1, which is 5, or 5/2, or 5/4. This is your list of suspects, right? This is your lineup. So we graph. Okay, so we have 4x cubed minus 10x squared plus 4x plus 5. In the calculator, I had to use x instead of t. Zoom number 6. What do we see? Oh, I only see 1. And, okay, which one does it look like it might be out of our suspects? Positive or negative? Let's see. I'm going to use the calculator to see if that's right. -0.5. 0. Okay, that's going to be right. But that's only one of them. How many do we expect to have? 3, because the degree of P of t is 3. Okay, so let's put the negative 1/2 up in the corner again. What goes across the top? Yeah. All right. And what goes here? Here. 2 or negative 2, yeah. Then here, negative 12. Here. 6 here.
10.
Here.
Negative 5.
As expected, we get 0 remainder. Now, what's the good news about the remaining coefficients? They're coefficients of what degree quotient? We started out degree 3. We divided by a linear polynomial, x minus, or actually it was x plus 1/2 we divided by, which corresponds to a 0 of negative 1/2. And so the remaining quotient has degree 2. So this would be 4t to the second minus 12t plus 10. And that quotient is going to contain the remaining zeros. So what do we do to find them? Well, first we set it equal to 0. Now, before you use the quadratic formula, what would make your life just a wee bit easier? You could factor out of 2, or since it's an equation, you could divide out of 2, because 0 divided by 2 on the right side is still just 0. So what do we get on the left side when we divide everything by 2?
2t squared minus 6t plus 5.
There you go. Okay, fill in the good old quadratic formula. Whoops, I said x out of habit. Should have been t equals what? Negative b plus minus square root b squared minus 4ac all over 2a. So fill that in. What do you get? Bless you. Minus 425. I like the way you said 4 times 2 times 5. That's the b squared minus 4ac right there. All over. There you go. So 4. All right, so that's supposed to be a 4 right there. It doesn't look like it. So if we do that multiplication, what do we end up subtracting from 36?
40.
So that's going to be what underneath the radical?
Negative 4.
-4. Okay. So we get 6 plus or minus the square root of negative 4 over 4. What's the square root of negative 4?
2i.
Okay. You guys remember how to simplify? So we get 6 plus or minus 2i over 4. You remember how to simplify that?
Go out of 2.
Okay, so out of where? The
top.
numerator. Okay. And then what's left in the numerator?
3 plus or minus I all over 2. Because the 2's cancel.
Because 2 over 4 is 1 over 2, right? So you could write this as 3 plus or minus I over 2 if you want. Does that make sense? Okay, I think we got them all. We've got all 3 because there were 3. So we've got zeros of what? Negative 1/2. And then 3 plus or minus I over 2. So these are your zeros. By the way, you can use your calculator to check these, even the complex ones. You just can't do anything with the graphing of the complex numbers. If a plus bi is a 0 of p of x, and p of x has real coefficients, then a minus bi is also a 0. You might have noticed this with the last problem. So this breaks down to 2 zeros, right? 3 plus I over 2 and 3 minus I over 2, which are really 3 over 2 plus 1/2 I and 3 over 2 minus 1/2 I. So these guys are conjugates. The idea is if you know 3/2 plus 1/2 I is a 0, then automatically the conjugate 3/2 minus 1/2 I is a 0. If you have real coefficients. Okay, and that's conjugate pairs theorem. P of x is equal to x to the 4th minus 2x cubed minus x squared plus 6x minus 6. Given 1 minus I is a 0 of p of x. So you're told 1 minus I is a 0. Find the rest of the zeros. Okay. Does this polynomial have real coefficients? Yeah, so conjugate pairs theorem applies. If 1 minus I is a 0, what's the conjugate of 1 minus I? 1 plus I is also a 0. But you start with 1 minus I. So you're actually gonna divide. Syntactic division works great with complex numbers, and you're actually going to verify, just like we did in the previous problem, you're gonna verify 1 minus I is in fact a 0. Up in the corner, we're gonna put 1 minus I, and we're gonna do the syntactic division. So essentially we're dividing by the quantity x minus the 0 of 1 minus I. So 1 minus I goes up in the corner, and then the coefficients, the usual 1, negative 2, negative 1, 6, and negative 6. Okay. So now we have to think about the process of synthetic division, which is why I've shown you so many examples. Because now we can work out this new kind of problem, I think, based on the fact that we've worked so many synthetic division problems. So the process is the same. You bring down this 1, and you multiply this 1 times the complex number 1 minus I, times the 0 of 1 minus I. And what is 1 times 1 minus I? 1 minus I. Now you're going to line up the real part, so you have a negative 2 up here, you're going to line up the real part of that product, 1 times 1 minus I, the 1 right here, with the negative 2 above it. And there is no, I mean, you can think of this as negative 2 plus 0i if it helps, but it gets messy if you write that. And then, so then you have the minus I off to the right. And then what do you do with that number? Always in synthetic division, what do you do with these two numbers? These two numbers, you always add. So you get, you add the real, so how do you add complex numbers? Well, you add the real parts and the imaginary parts. So negative 2 plus 1 is? Negative 1, 0i plus negative 1i is negative 1i. And then here's where you leave room for scratch work. Because now think about what you do. You take the 1 minus I times this result right here. Negative 1 minus I. But you don't want to, that takes a little bit of thought, so let's do it over here as scratch work. Actually, let me erase the extra stuff. Okay, so let's do it over here. 1 minus I times negative 1 minus I. And you think kind of like the FOIL method, right? It is the FOIL method. It's distribution. That's what the FOIL method is. So multiply the first guys together, and what do you get? 1 times negative 1? Negative 1. Multiply the outer guys together, and what do you get? 1 distributed over a minus I is minus I. The inner guys? Plus I. And the last guys. So plus I squared. Yeah. And then what happens then with these guys in the middle? They cancel out, and you end up with negative 1 plus I squared, but what's I squared? So you end up with negative 1 plus a negative 1? Or negative 2. So where does that go? Up. Right there. It's the same process. It goes in the same place where the multiplication would always go. Does everybody see that? Okay, negative 1 plus a negative 2 is negative 3. And you start the process all over again. 1 minus I times negative 3. So you distribute, right? Distribute negative 3 to the 1 minus I. What do you get? Negative 3 times 1 is what you're distributing. So you're distributing to the entire quantity, 1 minus I. So you would distribute the negative 3 to the 1 and get negative 3. Distribute the negative 3 over the minus I and get plus 3i. Fit it and try and fit it in there somewhere. And then add. So what do you get when you add 6 plus negative 3 plus I? 3 plus 3i. Yay. And you get to do this process all over again. Now, what do you expect to get right here when you do the multiplication?
6.
You better get 6, and you will, because if you factor out this 3, you're going to see that you're multiplying conjugates. So let's go ahead and do it, though. 1 minus I times 3 plus 3I.
Could you factor out the 3i from the second, or the 3 from the second little set? Factor
Yes.
it out, and then it would look exactly the way the other
Yes.
did when you were multiplying them?
You definitely could.
Okay.
Yep. So if you multiply the first together, what do you get?
3
3, the outer,
minus 3i.
well, the outer would be plus 3i.
Oh, plus 3i.
And then the inner would be the minus 3i as expected. And the last would be
Minus 3i squared.
minus 3i squared. And then you'd have, well, these guys knock each other out. So 3 minus 3i squared would be the same as 3 plus 3 as expected, or 6. And so you can use what you expect to catch mistakes. You know the remainder is going to be 0. You're told that. And I'm not going to lie to you. I wouldn't do that unless I asked you to check. Okay. So yeah, that's ugly. I admit it. That's ugly. But it gets easier from there on out. Now, 1 minus I was given to be a 0. We automatically know what's the other 0, or what's another 0.
1 plus i.
So now let's continue on with the division on the quotient with the conjugate of the last 0, 1 plus I. And this one will be easier because all the i's are going to go away in this step. Okay, so bring down the 1 and then multiply 1 times 1 plus I. What do you get? 1 plus I. And then look how nice this is. 0. Negative 1 plus 1 is 0. Negative I plus I, 0. Times 1 plus I? Yeah, it's still 0. Negative 3 plus 0 is negative 3. And then distribute the negative 3 to the 1 plus I. Minus 3, negative 3 minus 3i. And of course you get 0 there. Now we started out with a degree 4 polynomial. So these are coefficients. 1, 0, negative 3 are coefficients of what degree polynomial? 2. In fact, what is that quotient?
X squared minus 3.
Ooh, we know how to solve. We don't even need the quadratic formula. Set it equal to 0 to find the remaining zeros. And what will the remaining zeros be? Yeah. So x squared equals 3. If we add 3 to both sides, take the square root, you get plus or minus root 3, which is real. So that would show up on your calculator, but the square root of 3 is not rational. So notice I didn't use the rational zero theorem here. It wouldn't have helped us because there are no rational zeros. So what are the zeros, by the way? The zeros... Yeah, I'll go ahead and list them both, even though I was given one of them. 1 plus or minus I and plus or minus root 3. So the question is, how would you find the zeros of p of x equals x to the 5th plus 32?
Isn't that 2 to the 5th?
Well, negative 2 to the 5th would work. That's 1. How many more are there? There should be 4 others. So how do you find them? Well, guess what? You go back, and you guys are going to love this. You go back to Trigland. Yay! I know you guys were missing trigonometry. So guess what we get to do? We get to go back to Trigland for this example. But first, let's analyze what this is asking for. How do you find the zeros of a polynomial? Well, one way to get started is to set the polynomial, the formula for the polynomial, equal to 0, right? So what we're really asked to do breaks down to solving this equation. X to the 5th plus 32 equals 0. Or if you solve for x to the 5th, another way of thinking of it is we're asked to solve this equation. X to the 5th is equal to negative 32. Another way to think about it is to find, we really just need to find the 5/5 roots of negative 32. We know that there's got to be 5 zeros from the fundamental theorem, right? It's a degree 5 polynomial. And you know that one of them you get by taking the 5th root. of both sides. And so you get -2 for one of them. That's the real numbered answer. There's going to be 4 complex answers is what I'm trying to get at here. So what this breaks down, there should be 4 more. There should be 4 more zeros, and that's by the fundamental theorem of algebra, FTA. Okay. So it breaks down to this. We want to find the 5 fifth roots, if I could spell it right. We want to find the 5 fifth roots of -32. So now hopefully we understand the problem. Does everybody agree that's the issue here? How do we find these additional roots? Okay, well, I have to help you recall something. Recall. If you write a complex number in trig form, the shorthand for that, so if you have z equals a plus bi, that's standard form, right? A and b are real numbers. In trig form, it can be written as z equals r cis theta. Remember that? Where cis stands for cosine theta plus I sine theta. Remember that? Okay. Now r is the absolute value of z, which is the square root of a squared plus b squared. That's how it relates to the a plus bi form, right? And theta is the direction angle when you graph a plus bi in the complex plane. Theta is a direction angle. Okay. Does anybody remember a theorem that allows us to find the powers of r cis theta very easily when it's in trig form? Yes. R to the n cis n theta. The name of this actually has a name. This is Demois's theorem.
The power theorem.
It looks like de Moivre. That's what it's called. Well, it turns out that this theorem holds when you replace n with 1 over n, which represents the nth root. I'm not going to prove it, but this holds when you replace n with 1 over n. In other words, we could write it like this: r to the 1 over n cis theta over n. Now, I'm not calling this z to the 1 over n because there are a few representations of z to the 1 over n. Because the fact is theta is not unique, and you could keep adding. So to represent z up here, you could keep adding 360 degrees to the angle. And in fact, you could keep adding multiples of 360 because that's the period of the sine and cosine functions. So there's multiple representations in cis form. So I present this formula, but I don't actually think about it this way. I think about it this way. R to the 1 over n, cis, I think of it as theta over n plus 360 times k over n. And all that's telling you is that once you find the first one given by this formula, this is the only formula you need to recognize. If you use this formula to find what I would call the first root, even though we mark it with a subscript of 0, then all you have to do to find the subsequent ones is add in multiples of 360 over n. And that will help you find all of them. So I know right now it's all a blur what I'm talking about because you need to see an example to make it make sense. Find all 5 zeros of x to the 5th plus 32 equals 0. So really, when I say find the zeros, we're talking about p of x is defined as that polynomial on the left side. And i.e. find the 5/5 roots of negative 32. Okay, first thing we have to do is convert negative 32 to cis form. So, okay, so z equals negative 32. If you graph z equals negative 32 in the complex plane, you'll see how to convert it to cis form without using the formulas. So remember, in the complex plane, the horizontal axis is the real axis, and the vertical axis is the imaginary axis, we'll call it. But negative 32 is over here on the real axis, right? So we need an r and we need a theta to put this in r cis theta form. What is r? What is the distance that negative 32 is from 0? 32. So r is the absolute value of z, which is positive 32. The absolute value of negative 32 is positive 32. What's the angle? You can see, without using the formula tangent theta equals b over a, you can see what the angle is. The angle is 180. Theta is 180. So z in trig form, you're going to have to convert to trig form. Z in trig form is positive 32 cis 180. Does everybody see that? And which stands for 32 times the quantity cosine theta plus I sine theta. Does everybody see that? Now let me show you how easy this actually is. All you need to remember is the original formula I showed you for z to the n, which is r to the n cis n times theta, which is the one you memorized before the last test. And then remember, oh, I'm finding roots. So one value of z to the 1 over n, so one value of the nth root of z is r to the 1 over n cis theta over n. So if you remember that formula from before the first test, you can derive the formula you need to use to find these roots that you're looking for. Okay? In this case, what is n? It's the 5/5 root, so n is 5. Okay? So let's find what I'm going to call, I'm always going to call that first root the root you get. So this guy, this particular one gives you the first root w naught, w subscript 0 we call it. Okay. So let's fill it in. 32 to the 1/5, right? 32 to the 1/5, which is 2. Cis, okay, what's the angle? 180 over 5. So does everybody see I'm just filling in this one and only formula you need to memorize? Or derive from the original version of de Moivre's theorem. Does everybody see that's what I'm filling in? Okay, so let's simplify that. So that means w naught is 2 cis, what's 180 divided by 5? 36? Okay. Now that's just one of them. There are 4 others, right? So that little talk I was given that you probably didn't quite, it probably wasn't quite clear. It never is the first time you hear it. You can get the others by adding multiples of 360 over n. That's the trick. But that's just going to be 360 over 5 added consecutively. What's 360 over 5? So 360 over
72.
5 is 72. So if you add in multiples of 72, you'll get the other zeros. Add in multiples of 72 degrees to get the other zeros. Before I answer your question, let's go ahead and finish this up. To get other zeros. Okay. So, well, that's easy enough. So what I would call W1 would be obtained by simply adding 72 degrees to 36. So what does that give me?
108.
Yeah, and if it's a particularly difficult thing to add, here's a cool way to do it on your calculator. So we could figure out how to add 72 because you just add 70 to each one and then add 2. That's easy enough, but let's say it were a difficult one. So where are we starting at? We're starting at 36. In your calculator, enter 36 and then go plus 72. And there's the 108, and then just keep hitting enter and it'll keep adding 72 and get you the other ones. Okay? So not that we needed it for this one. If we think real hard, we add 72, we'll get 108. So how did I go from this angle to this angle? I added 72 degrees. Okay, and then we only have 2, so we have 2 more. W2 is going to equal 2 cis. If you add 72 to 108, what do you get? 180. Is that the one we already knew about? That's negative 2. 2 cis 180 is negative 2. Okay. And then we have one more. So we added 72 to get to the 180. And we'll get the last one. Oh, wait. No, I'm sorry. I was thinking we only had 4. We only have 3. We have 2 more to do. So W3 is the second to last one. 2 cis, add 72 to 180. What do you get? Not 152, but 252. So add 72 again, and then W, since we started counting at 0, W4 is the 5th root. So W4 is 2 cis, add 72 again. What do you get? 324? Okay.